Today, I'm going to show you how to use machine learning to support infrastructure investment planning for water and natural gas pipeline systems. Machine learning is a field of computer science that often uses statistical techniques to give computer systems the ability to learn with data without being explicitly programmed. In our case, the learning data is a history of failures, breaks, leaks, incidents, and defects found on pipeline systems. So most water and natural gas systems were constructed in the early and late 1900s, and they're starting to show their age. For example, each year there are more than 250,000 water main breaks or leaks on the estimated 1 million miles of water mains. This equates to about one break every 4 miles per year. It's been estimated by the American Society of Civil Engineers and other stakeholder groups that billions of dollars a year will be required to ensure an ongoing, reliable, safe supply of water and gas to consumers. Investment resources, though, they're limited. So the challenge is determining where to invest, how much, and where and when to invest. So machine learning can support optimal investment decision making, and this is really what I'm going to talk about in this webinar. Machine learning is a process. Historical data regarding breaks and leaks are used to learn models. Learned models then can be applied to assets of similar type. The results of the application of these models are expressed in terms of predicted break and leak rates over time. We can then monetize these rates over time by combining them with consequence data. As I previously mentioned, we use RapidMiner to support the learning processes. Although there are several applications in the market, RapidMiner really meets our needs based on its ability to integrate with disparate data sources, ease of deployment and use, its low cost of ownership, and its ability to scale to more complex problem solving as required. Before we get into the details of the process, let's take a look at the results that come out of this. Predict future breaks and leaks. The actual output from machine learning is a confidence value expressed from 0 to 100% for each segment of pipe. We look at these confidence values as how susceptible the pipe is to failure. These confidence values are combined with Weibull-based condition curves to predict breaks over time. We then combine these breaks over time with consequence event costs. This gives us risk values expressed in dollars for each pipe segment now and in the future. We can look at these risk values as the total variable cost of the ongoing ownership of the asset. Discounting current and future cash flows to time zero supports comparative investment decision making. So these infrastructure investments can then be assessed as to their ability to reduce this cost or the cost of ownership. Understanding this concept allows us to use machine learning to support what to invest, when, and where. Now, if we take the result set and put these on a map, this tells a pretty good story. So here's a typical distribution system, water distribution system, where the blue line represents the pipelines, and there's different properties underneath each one of the line segments that I'm showing here. Risk results are expressed in dollar per foot per year. As we filter these values, we can see the parts of the system with higher variable cost of ownership. So you can see that the pipelines that have been filtered out are lower risk. Higher risk pipelines still show up on the map. This gives us an idea where the pipeline segments are with the highest opportunities for reducing risk. We can also filter these pipelines by failure prediction, or I should say failure prediction confidence. So as we scroll this failure prediction to, let's say, 31%, this is saying show all the pipelines that have a 31 to 85% susceptibility to external corrosion. We could have picked any of the four failure types that we're managing here. This is just to show and highlight the areas where susceptibility is high. So this gives us an idea of what the mechanism is that's driving the particular failure type. And this would lead to decision making on the type of project that you might want to implement to minimize the risk. Lastly, recall that the machine learning models are learned by historical data. And if we want to see what the historical data looks like, we can pick, let's say, for example, the failure type external corrosion, and pick where the breaks have happened over the last several years. And you see these are the break segments, or the segments where the breaks occurred. And this is what we're learning from. Call our machine learning process here. We are gathering historical data about breaks, leaks, and failures. And we are processing these through different methods to learn different models. There's also data that would be associated with these breaks and leaks. We call that data attributes or features. Features are usually identified by the subject matter experts, those that are most familiar with the types of failures and the system that's involved. Data management involves pulling all of this data together, not only the historical failure data, but the data underneath, the potential correlating and influencing data behind that failure data. For data management, we use RapidMiner as the primary tool to prepare the data sets for learning and for predicting. So let's take a look at RapidMiner. So this is the desktop version of RapidMiner. And for more information and tutorials and even to download the software, there's a free version that you can load and use. You can go to rapidminer.com. For our purposes here, I'll kind of give you the highlights. We organize the machine learning processes in this repository. So these are folders of different processes. And these processes are comprised of operators. We have these operators that serve their purpose, for our objective, or what we're just trying to accomplish within the process. These operators, if you look on the right-hand side, are associated with help and tutorials and other information, and they may have parameters associated with them too. So you need to understand what the parameters are about, how to set them, and a little bit about the purpose of the operator. All the operators are in this operators tab, of which there's hundreds of them, and they just perform the tasks or the heavy lifting within the different processes. Enabling these operators is simply a matter of selecting them within the operator, the repository here, and just dragging it and dropping them and connecting them together. So we've created a lot of different processes in sequence for preparing our data for learning and for prediction. Let's just walk through a few of these processes. So the first process we have is simply reading a database, and it was the database that was underneath the map that I just showed you. Then there might be additional data to join to that data. So if we take a look at a typical joining process here, we're reading a database and then grabbing break data, joining it together, and then storing it off for local use. We pull all the data together and we eventually arrive at this process. But what this process is doing is creating a data set for each one of the labels, each one of the targets that we're concerned with. In our case, there's 4 failure modes that we want to learn from. So we're reading a prepared data set. We're gathering information specific to this target here. So these are the attributes. Those on the left, that's what's available, and what's on the right is what's been selected for that data set. We set the role, so we set external corrosion, the evidence of the failure or the incident as the label, and then we store off the data set and write it to a database for ongoing use. Now, I skipped over one process here. Let's take a quick peek at it, where we're joining all the data together. But you see there's operators for doing things such as replacing data, imputing data, replacing missing values, maybe generating different attributes that we're interested in. Pull this over here. Okay. So this is kind of like a cleanup phase to make sure that the data set meets all the requirements of the learning that's required of it. If we want to take a look at a finished data set, let's go to the local data repository here, and we will pick external corrosion. And what this does is brings up the data set for external corrosion, and it shows you what we're learning from. So each one of these rows here is a pipe segment, and it's indicating if a failure was observed in that segment or not. And then if a failure was observed or not, there's associated features or attributes about that pipe segment. So this is what we're learning from. We want to reveal the underlying patterns that have resulted in either a failure happening or not happening. It's also useful to go through the statistics here to kind of look at the high and low values and how the attributes are organized for each of the types of features. We also can look at missing data. Some of the methods we use don't like to have missing data, so we try to impute, infer, or remove data that might be missing. Then lastly, we want to just visualize the different data we're looking at here and do a little bit of analytics on it. As it sits natively, we can do that. So what this is showing is that external corrosion failures have happened more with cast iron pipe. A nice feature within RapidMiner that's fairly recent is called turbo prep. So if you don't want to go through the processes that I just showed you and you simply want to connect data together and clean it up through more of an automated process, that's what turbo prep does. So a couple things here is you can look at a table of data, just select a table of data through loading the data, and then you can examine it by showing the details, and you can walk each attribute and see its distribution, as well as some quality assurance metrics here on the left. I won't go through what these all mean, but these would indicate maybe some corrective action is required to use that data set for learning. If some kind of corrective action is required, then we have tools up here for transforming, cleansing, generating new data, and merging data. So it's quite a useful tool if you want to very quickly pull together different data sets, clean things up, and get it ready for learning. So lastly, we go through these processes here for each one of the targets that we care about. And then we also go through the similar processes to create prediction data. Okay? So these would be the same or other assets of similar type that we want to generate data sets for that we would eventually want to apply our learned models against. So we want to do predictions against similar types of data or similar types of assets. So that's what that's all about. Okay, now that the data is ready to go, we use what's called feature analysis methods to understand the potential influence or importance of data to the prediction target. We can use these methods to reduce the amount of data required for learning, impute missing or unknown data, or determine if just additional data elements are required. Now, although there are a lot of methods available, I'd like to show you information gain, correlation, and one of my favorites, an evolutionary genetic algorithm approach. Okay, so back to RapidMiner. Let's close these folders for data management, close our local repository of data sets, and we'll expand out our feature analysis folder. Let's first take a look at information gain. So information gain takes the data sets that we just prepared, and depending on the target, in this case external corrosion, it will determine information gain for that target based on the data that underlies that target, gain ratio, and Gini index. And there's different operators for preparing this type of information, but let me just run this process so you can see the results that come out of it. So that was pretty quick. You can see that for external corrosion, if that's our target, given the underlying data, information gain is calculated with these values between 0 and 1. 1 and near 1 are attributes that have good influence on whether or not external corrosion could happen or not. And it's all based on history. So this is showing that pipe age, material, joint type, depth of cover are probably more influential historically than, in fact, external coating, road class, frost, etc. This gives you an idea of the importance of the attributes that have underlied the threats or the defects that you're trying to model. Now, let's take a look at correlation. So correlation is similar, but in this case, it doesn't need a target. It's just looking at how do all attributes correlate together. So let's run this and see what it tells us. Okay, so this is a correlation matrix. And what this allows us to do is take any attribute and develop a pairwise with any other attribute. So this becomes useful if, for example, you have two variables A and B, and maybe on one pipeline you're missing B but have A, and another pipeline you're missing A but have B. And if you know A and B are highly correlated, you can use one or the other for the surrogate for one or the other. So that's one way to use it. Correlation is also valuable when you're looking at certain machine learning methods because they don't perform very well with a lot of highly correlated data. So we use correlation analysis really to support those two cases that I mentioned. The last and my favorite is optimizing the selection through a genetic algorithm. So what we're doing here is we're reading the data set. In this case, it's external corrosion. Okay? We're picking data that we believe is important to the influence of external corrosion. And I'll skip over these two steps here. We just don't have time to get into sampling. Then we apply this optimize operator to that data set. So let me just run this so you can see what's happening. So what we have here is on the x-axis, we have the objective that we're seeking, like how well do these attributes meet what our objective is: sensitivity, accuracy, specificity. And here are the number of attributes that would be required to meet that objective. So what this is showing us is that in this case right here, you need 8 attributes of a specific type to achieve a 99% plus sensitivity. If you increase this up to 11, you might only get up to 99.6 or 7%. So we call this a Pareto front right here. This is just showing us that the number of attributes, as they increase, your objective, like the model performance, improves. But there's some balance here. There's some optimal place to be and to use. So maybe if this model had 20 different features associated with it, and our objective for sensitivity was somewhere around this range, then maybe just using 7 out of those 20 variables would be enough. Let us take a look at our specific results here. So each one of those points is represented through this grid. And what this is showing us, if I sort sensitivity from high to low, we can see that these 8 features here can generate this sensitivity. Now we could use 11 features to do the same, but why not just use 8, given the cost of data? Expand this open, and you can see the 8 different attributes. So I mentioned sensitivity and accuracies, and for those that are not familiar with it, let's take a look at the confusion matrix. The confusion matrix is one type of performance vector for learned models. So this represents the performance of a model that is learned. And we call out accuracy, in this case 89%, as indicating how well the model predicts versus actually what is out there. This model performance is determined through held back data, so test data where we know what the outcomes are. And we're simply comparing the actuals to the predictions. So many times in the pipeline world, we focus on sensitivity. Sensitivity is a good representation of the amount of misses that the model would produce. So what this is saying is the model predicted 1 miss because this was actually one miss, and it did predict it as no defect in the pipe, whereas it did predict 9 defects in the pipe that were actual defects. Many times you sacrifice false positives for minimizing misses. So if you can accommodate more false positives, then you might go down that road because there's a cost difference between the two. When we get into the actual machine learning and I show you different methods and models, we'll have a confusion matrix associated with each one. Okay, so now we have a basic understanding of the influence of underlying features and what data we should use to learn our models. So we're ready to move on to method learning and selection. With method learning and selection, we have a lot of machine learning algorithms or methods to choose from, probably hundreds. For our use case, we want to use methods which would provide us, of course, the desired results, but at the same time being transparent and easy to explain to domain experts and business stakeholders. So more specifically, we're using several binomial classification methods and complementing these where appropriate with regression methods. So I'm going to show you Bayesian methods, decision trees, regression, and we'll also use a little bit of neural networks. But you'll see with RapidMiner that there's operators for each one of these things, so we can plug these into, as many of these into the processes as we'd like. Let's return back to RapidMiner, and we'll get out of this approach here and go now to evaluating models. And let's open up external corrosion. So you can see what we're doing here is we're grabbing the prepared data set, setting our role as external corrosion, that's what we're predicting. We're selecting attributes as part of that data set. In this case, we're just picking all of them. We could have used a previous feature analysis as inputs to this attribute selection. But in this case, we're just going to use all of the attributes. And for this webinar and demonstration, I've just enabled 2 methods we're going to look at: naive Bayes and decision trees. This operator here that we're looking at is what's called cross-validation. So I won't get into a lot of detail, but this enables us to generate the performance vectors that I just showed you. It's going to give us some validation values that will then tell us how good the different models are. Well, let's run this process and see what our results look like. So I just ran it for decision trees to show you what the outputs look like through the process. We took the prepared data set where we had some knowledge of where external corrosion was happening and the underlying data. Okay? So these green columns here are showing us that, on this one here on the left is showing us the actual occurrence based on history, and the prediction column is the prediction whether external corrosion would happen or not. And that prediction is based on these confidence values. So this is what we are really using in our process. Confidence true just means the level of susceptibility, or how confident we are that this underlying data here would drive to an external corrosion failure. If it exceeds some threshold, we end up with a true, and if it's below a certain threshold, it's a false. Now, for our purposes, we're using these actual numbers here within the risk formula that I showed you. The learned model that came out of here looks like this. So this is just a decision tree, real easy to explain, sometimes easier to just show it as a grid of rules. So the same thing as a tree. But this tree, this represents what has been learned about external corrosion, true or false. Then we have an associated performance vector. So the confusion matrix that I just showed you, this is the same thing here, showing that this model generates a sensitivity of 99.14%, indicating 37 misses. and 1,014 false positives. This is one way to take a look at the performance of the model. And as you go through the different methods in learning and you have all these different performance vectors, this allows you to tweak the parameters and come up with the best learned model for purposes of future predictions. Now let's return back to the process and let's take a look specifically at the decision tree. And you'll see when I select this operator on the right hand side, we have these different parameters. These parameters can be determined by a data scientist expert, so you can vary these up and down to try to tune your performance. But another thing you can do is you can simply just optimize these parameters through another process. Let's take a look at this operator, and as you might expect, it's called optimize parameters. When we use this operator here, and I double click and open it up, and open up the cross-validation process, you'll see that we have a decision tree in here with the same parameters to be set up. We can ask this high-level process here to optimize the parameters within the different operators that are underneath it. So if we pick the decision tree here, you can see we have different parameters we can optimize on. We've picked the maximum depth. So in this case, we wanted to figure out what is the maximum depth setting parameter that will give us the desired performance. So you cancel out of here and just run it. What this is showing us is if we care about sensitivity, sort this from high to low, you can see that the decision tree depth, the maximum depth, should be about 9. And we can do this for every parameter that's part of, really part of every operator, and get a good idea of how to set things up. If we're not an expert data scientist, we can use this operator to guide us on the best decisions there. And lastly, other than the performance vector, the confusion matrix, let's take a look at ROC curves. So you may have heard of these before, but the receiver operator characteristic curves, we can generate these for all the different models that we just created in this folder number 4. You see when I run this, we get a set of ROC curves for each data set and for every model. Now all the ROC curve is doing is showing us a cumulative true positives with a cumulative false positives. And what we're looking for is the greatest AUC, or area under the curve. That would be the better performing model. So naive Bayes in this case, the blue lines, is the poorest performing model when we're looking at internal corrosion. And it looks like the green model, deep learning, might be our best, but maybe gradient boosted trees might be the best. So you have a choice here on what to use, because these would be the higher up curves. So the curves that are at the higher, that go to the higher to the left, would represent the better methods to use for the learned model. So at this point, we've integrated the data that we believe is important. We've created data sets. We've learned about these data sets and the underlying attributes. So we know what features, data, attributes, variables are important to the process. We've also selected different methods, and we've run our data sets through them to create different models. Each model has its confusion matrix or its performance vector. So we have a pretty good idea of what the best models are to use for the particular targets that we care about. So we're ready to deploy these models and actually do some predictions. So let's move to that next step. Okay, so as you might imagine, we have a folder for predictions, and we have a prediction process right here. It's quite straightforward. So if we pick, let's say, Bayes as our best model for external corrosion, we simply get that model from a previous folder. Then we read the prediction data set, the data that was prepared for the assets we are interested in doing a external corrosion prediction against, and we use this model called apply model to generate results. The results look like this when we run the process. Each one of these rows being a pipe segment. And let's just look at external corrosion and look at bays since we did pick that. So for each pipe segment, we now have a true and a false value or level of susceptibility to external corrosion. And what we might look at here are the pipe segments with the highest susceptibility. And the reason they're high susceptibility is because of the underlying data. So the final step is to apply the selected learned model against the assets we want to predict failures and risk. What we're going to do is generate susceptibility levels for each one of the threat types, each of the targets, and we're going to plug them into this probability function. Okay? The function uses the machine learned susceptibility, benchmark event rates, and condition curves to come up with a probability or an events per foot per year. We then multiply this times consequences, dollar per event, so the cost of the break to the utility, customers, and other stakeholders, and that results in a risk amount, which is dollar per foot per year, and this becomes our main criteria for investment decision making. Performing predictions with RapidMiner is pretty straightforward. You can see we have an operator here which is just retrieving an object. This object is in this case is the naive Bayes model for external corrosion that we just learned, and we use this operator called apply model by applying the model to the prediction database. So these are the assets that we want to do a prediction against and see what the level of susceptibility is for external corrosion. These other downstream operators here, this is really about preparing the data for downstream use. But the main concept is simply just applying the model to the data. Let's take a look at what the results look like. So here's typical outputs. So these would be predictions for all the different pipe segments. And if we go take a look at external corrosion and look at Bayes, we can see here that these are the levels of susceptibility. These are the values that we use in our risk function. We sort these high to low. The numbers with the higher numbers are going to be higher susceptibility to the presence or non-presence of external corrosion. And then scooting all the way to the right, you can see the influencing data for that prediction. Let's again go back and take a look at these on a map. So here's our map where we applied, in this case, let's see, gradient boosted trees. That's our learned model for external corrosion. And if we want to see what our prediction confidence levels are between, let's say, 28% and 85%, we can filter that out. And now we can see the pieces of pipe that are predicted to have a higher level of external corrosion susceptibility. Now we could have picked an entirely different distribution system that we didn't learn from and applied the models to. I'm just showing it this way for convenience. Another useful feature that RapidMiner has is the ability to do some sensitivity analysis on the susceptibility values or these confidence values. So if we go through here and pick a group of pipeline segments, what it is doing for us now is telling us what's driving the prediction, what's contradicting the prediction. So those pipelines that I highlighted and selected that were of higher susceptibility, the reason they are higher susceptibility is because of joint type, material, presence of a railroad. And what's driving them in the other direction is going to be concrete corrosivity, diameter, and pipe age. So this gives us some good input into what specifically is driving the threat. And then this gets associated with the types of projects that we might implement to reduce risk. So bottom line is we have a process and approach here that supports the investment decision making. It's all about figuring out where to invest limited resources, when to invest them, how much to invest, and then what types of projects to invest in. We now move to our final step, which is financial analysis. And this really deserves a future webinar, which we'll probably do, but the concepts are fairly simple. So let's take a look at these. What this slide is showing is we can pick any of the groups of pipe segments that I showed you on the map, and we can show what their risk is over time. So this is one way to do it. This is just showing cumulative dollars of risk for one or more pipe segments. So this becomes our opportunity. If we had a brand shiny new pipeline that had all the mitigation in it, maybe this risk would not be here. So if you had that brand new car, you'd have no maintenance theoretically for the next 5 years. But what we're dealing with is old pipe, and we would expect to have leaks, breaks, and other events that introduce risks that cost us money. So representing your assets in this manner gives you an idea of what types of projects, where and when, at what point in time to invest in. And that's what this graph shows here. It simply shows that if you propose a particular option to reduce risk, you want to replace the pipe or rehabilitate the pipe, you can run it through the same risk function and come up with a reduced risk value, because supposedly the project will have associated with it a smaller number of failures or events now and in the future. And that would be reflected in this yellow section here, which is the benefit of the spend. Then you can use all kinds of financial techniques to calculate the benefit cost of doing a project, make the investment versus the actual benefit. Or you can look at break-even cash flows, break-even net present values, and other types of metrics to help you figure out what places should I make my investments and what should I invest in. So hopefully this has been useful, showing you the entire process of machine learning. There's a lot of detail to it, but what I showed is really the fundamental elements. And what we're driving towards here, again, is better decision making on constrained financial resources.